Okay, I'm going to add one more video to the list for chapter 3. I'm going to call this uh, chapter 3. Too long, didn't watch. Really, what this is just a summary of chapter 3. I have a periodic table next in the next thing, but again, this is more just a summary that will help you kind of connect all of these ideas and kind of put them all in perspective. So, chapter 3, we started with matter. So matter is broken down into a bunch of different categories. Again, we take matter, which again, matter is defined as something that has mass and takes up space. Okay, that's what chemistry is looking for, is how to discover matter. Matter is broken into two categories, into pure substances and mixtures. Again, a mixture is nothing more than just a combination of one or more pure substances. So if I have salt water, for example, I have water, I have salt. Those two things together make a mixture. So if you have something that's pure, we can focus on it solely. That's going to be a pure substance. And then pure substances are broken into two categories. And all of this really has to do with how many chemicals are present or how many elements are present. So pure substances are in the form of elements, and we define an element as only one substance or only one atom, type of atom. Okay, carbon, all carbon, it's all gold, it's all sodium, whatever it happens to be. And compounds. Compounds are two or more elements present. So sodium chloride, for example, which is table salt. Okay, it's got sodium, it's got chloride, but it's always in the same ratio, one of each. Water is the best example, probably. Water contains two hydrogens, one oxygen. It's always going to be the same. And then mixtures, we have two types of mixtures: homogeneous mixtures, homogeneous, and heterogeneous. So a homogeneous mixture is going to be something that is visually indistinguishable. So salt water, for example, you can't see the differences in locations, but heterogeneous, something like dressing, where you can see, oh, here's clearly some oil here and some vinegar there. The top is not going to taste the same as the bottom, but if you had salt water, they absolutely would. And again, you can always separate a mixture into its pure substance by some physical process. And we're going to do this, but physical process, if you have salt water, you can just evaporate the water. So the mixture being salt water. If you evaporate the water, you've got the salt that remains behind. You separated those two into water and salt, done through just evaporation, which is a physical process. A compound converting into elements, this has to be done chemically. I can't take water and evaporate it and all of a sudden it's going to become hydrogen and oxygen. You have to electrolyze it. You have to put it through some kind of chemical process, and that's how you're going to end up in that situation. Okay, so matter is broken up into these different categories. And with that, a physical process and a chemical process, we have to recognize that we have two different categories of processes or phase changes, right? So a chemical change or property versus a physical change or property. Okay, chemical basically means that the chemical, whatever chemical or compound, I should say, or actually chemical can be element too. So a chemical will be different after. So after you run a process, right? So if I burn wood, it was cellulose to start. So a bunch of carbon, hydrogen, oxygen together in this fixed ratio. It was a molecule before, and now it is just carbon and water. Okay. So chemical change, you had the wood at the beginning, you don't have it at the end. Sugar, if I burn sugar, sugar starts as sugar, it ends up as something else. Okay. It's no longer sugar at the end because now it's burnt. A physical process is just simply the substance will change forms. So it goes from gas to liquid, liquid to gas, some version of that. So chemical versus a physical property, and that's kind of what we're looking at there. Next up, let's just briefly talk about these transitions. So solid, oh, actually, this is how I did it before. Solid to liquid to gas. Do you remember solid to liquid, liquid to gas, liquid to solid, gas to liquid, and then the whole thing? Okay, so each of these processes have a name associated with it. Solid to liquid, we call that we would call that melting. And I would totally know what you mean when you said melting, or actually the more chemically proper one, weirdly, is fusion. Melting is going to be okay, but recognize fusion is another word. Going back from liquid back to solid, we would call that freezing. And that's good, okay? Next up, liquid to gas. Evaporation, that one is fine, but what I really would rather say is vaporization. Vaporization, yeah, vaporization is more appropriate. Evaporation typically talks about water, and we're talking about vaporization. We can talk about that about anything. Gas back to liquid is condensation. And for any of these, just simply think about something going through that process, right? Going from water vapor to, liquid water on the outside of your glass, you would say, oh, it's condensating. So you kind of come up with that on your own. Solid to gas is sublimation. And the hardest one to remember is gas to solid, deposition. This is actually timely. We have a bunch of forest fires right now. And those forest fires are depositing the highly the soot and whatnot. They're depositing it on trees, cars, cables, or buildings, that kind of stuff. So it goes from a gaseous form and it deposits it as a solid on these surfaces. It doesn't turn into a liquid first. Okay, so those are our changes. Okay, physical, chemical change or property. And among those properties, we have to recognize we have both intensive and extensive properties. An intensive property is independent of amount. So an intensive property is going to be something like density, where density is always going to be the same. The density of water will always be the same regardless of how much you have of it, right? But something like volume is going to depend on the amount, and that is what an amount. There we go. UNT. There we go. That's going to be dependent on the amount. So extensive property would be something like volume, mass, those types of things. Okay, good. All right. So moving on. So this is the basics of the matter, understanding matter. Okay, so summary of chapter 3. Matter is broken into a bunch of different categories, physical and chemical changes. We can identify them, and we know about phase changes, and we recognize the difference of something changing forms, right? So all of these right here are going to be physical. All of these guys right here in the middle, these are all going to be physical changes, okay? Or boiling point, talking about the boiling point of water is going to mention something about the physical property of a substance. But a chemical change might be something like sugar burns, right? Sugar burning basically says that it starts as sugar and it ends up as something else. Okay, next, let's just talk about the atom. Let's just make this really simple, okay? So we can ignore all of the experiments they did way back in the past, and we can just simply say this. I have a nucleus. The nucleus contains one, let's say, we'll do 3. We'll do 4 of these. Those are going to be my neutrons. The blue ones are going to be my protons. Okay, so in the nucleus, I have a bunch of mass. This is where all of the mass is, right? Protons and neutrons, they all have a weight of 1 AMU. That's their mass. Okay. On the outside, I have a bunch of electrons. We're just going to E minus, we'll do 3. Nah, we'll do 4. We'll do E minus. So the little E minus are the electrons. The electrons they weigh nothing, 0 AMU. Okay, their mass versus the proton relative to the protons and the neutrons is non-existent. Okay. Okay. So that's great. This is what our atom looks like. There is a ton of empty space in between. The nucleus is much smaller than this. Nucleus would be like this, and then our orbit would be significantly larger. So just keep in mind that all of that mass is stuffed in the nucleus, and all of this part here is just simply empty space. Even the electrons is considered empty space because they don't weigh anything. So the nuclei, if I had a bunch of nuclei together, there's a big gap between where you're going to actually find mass. So there is nothing in between. If there's nothing in between, electrons can hang out here, all sorts of stuff, matter can go through there, and it's not going to matter. Okay. So the nucleus is composed of all of that stuff. Within the nucleus, within the atom, we're interested in two things. We're interested in the mass and the charge. So when I'm defining this thing, I know that, again, I have 3 protons. Having 3 protons is going to define what element it is. Okay, if I look at something with the atomic number of 3, that is going to give me lithium. So whatever this is, the thing that I just made, it is going to be called lithium. And so I will simply say this thing here is Li. That's the symbol that I'm going to use because it has an atomic number of 3. So this is my lithium. Those two things are always linked together. The number, the atomic number, the number of protons, and the number of neutrons. Or I'm sorry, and the number of, and the name of what we're looking at. All right, so it has 3 protons. The other portion of the mass is it's going to have 4 neutrons. Those two together give me a mass equal to 7, right? Add those two up, and I have a total of a mass of 7. So this right here is going to have a mass of 7. Again, the other ways that I could say that, Li7, 7 Li, lithium 7, all of those work, okay? The last part of this is charge. So this over here is mass, number, symbol. Remember, these two things are always linked, mass and the number, or the symbol and the number. And then the last part here is charge. And what we have to think about is we have to remember that electrons have a charge of -1. Protons have a charge of +1, and neutrons, no charge. What that simply means is I'm going to add the total that I have. So I have 3 protons, which equals a +3 charge. I have 4 electrons, you see them around the outside, a -4 charge. Add those two together, and you end up with a -1 overall charge. So this thing would have a minus, we would write minus or -1 minus, but it would have a minus charge total. Okay, so we can always look at a symbol and determine protons, neutrons, and electrons based on all of this information. Okay, so just 2 quick examples, or I guess 1 quick example. Carbon 12, I know that has an atomic number of 6, so it has 6 protons, neutrons equals 6, because both of those numbers have to add up to give me the total mass. And then electrons, well, notice that it has no charge up here in this corner, So that means that the number of positive charges equal the number of negative charges, so we have to have 6 of each. Okay. Yeah, that's pretty much it. And then finally, let's do one more. Let's just say magnesium 2+. So if I look for magnesium, we see it down here. Magnesium has an atomic number of 12. And I'm going to give it a mass now too, I suppose, because I didn't before. So magnesium has a mass number of 12, so protons is equal to 12. Neutrons, well, 25 minus 12 is going to give me 13. So I have 13 neutrons and electrons. All right, so I know that I have 12 positive charges. How many negative charges do I have? Well, notice that I have 2 extra positive charges present, meaning that every single one of those protons need to go away, except for 2 of them need to so we have 10 electrons. So 10 plus 12 minus 10, if I add those 2 together, I end up with a +2 charge. That's going to equal the charge overall. Okay. All right. So we don't need to know any of the experiments. I mean, know the Rutherford experiment, understand kind of that they discovered the electron and cathode ray tube and all that. But the really important stuff is nucleus, tiny mass in the center, electrons are around the outside, which we're going to see in the next chapter anyway. Mass, all is in the nucleus, is protons and neutrons, protons and neutrons, protons and neutrons, and the charge is just simply the protons and the electrons, which one is greater, right? If I have more electrons, it's negative. If I have more protons, it's positive. If they're the same, it's neutral, okay? All right, and then finally, the periodic table. We have, and I'm not going to go through all of these, I'll just mention them now, but group 18, the noble gases. Group 17, the halogens. Okay, group 1, the alkali metals. Group 2, alkali earth. Okay, or alkaline earth. Both of those would work. I'll just name them alkali metals. 2, alkaline earth. Metals, because that'll lead us to our next comment. Noble gases. And then finally, halogens. Okay, great. Notice where the metals are on the left-hand side. That's why we have the alkali metals and the alkali earth metals. And we know that this happens between here. So we have this little ladder here. And this is where all of our semi-metals exist. So metals on the left-hand side, metals, non-metals, right? Semi-metals. There we go, we can do this. Semi-metals, or sometimes called metalloids, but it's all of the ones that are on that staircase, all of the purple ones in this case. Down a group. Okay, so all of these columns are groups. They have the same, or similar, I should say, chemical properties. Okay, so down a group, similar chemical properties. Across, we call this a period. And the number is out front. Okay, so group 1 is really reactive with water, and that's what we find out when we run chemistry on this stuff. Okay, and that's pretty much all that you need to know for all of the different periodicity. You just kind of have to have this out. We're going to break it down more in the next chapter, but that's the basics of it. Matter, periodic table, how it was developed, and kind of what an atom looks like. Okay, all right.